Hello, this is Professor Dan Kernler. This is another video in our Calc 3 series. In this video, we're going to talk about how to determine whether a critical point is a relative maximum, relative minimum, or a saddle point. The first example here, it actually refers back to the previous problems that we have done. So what I'd like you to do right now is take a couple of minutes and go back to examples 1, 2, and 3 and compute all the second derivatives at the critical points that you found. So pause the video, should take you maybe 10-15 minutes. Great practice for second derivatives, second partial derivatives, mixed partial derivatives, all three second derivatives. Evaluate them at those critical points that we found in the previous video. All right, so hopefully you actually paused that and did that practice. Let me fill these in here. We should have had, oops, gotta have the drawing tool, 2, 1/2, 0, and -1/4, -1/4, 0, and -2, 1/2, and 0. So now if we think about these, remember the second derivative in Calc 1 gives us concavity. So this is really the concavity in the x direction, the concavity in the y direction, etc. And so what happens here, whether these are maximums or minimums. So let me pull up a maple file here. See if I have this one up, not that one, this one. So here we have the first example, and there's our point, 2, 4, 3. And second example, 1, -3, 2, we can see there. And then third example, it's kind of interesting. We can see here on the first example, if we look just from the x direction, I don't know if I can get this perfectly lined up. Oops, sorry, that's the y direction. You can see concave up. In the x direction, concave up. Makes sense, it would be a relative minimum. Here we have the second example. If we look just in the x direction, concave down, just in the y direction, also concave down. Makes sense that it would be a relative maximum. And then, so the first one's relative minimum, then relative maximum, and now we have kind of a mix. We have concave up in the y direction, and then concave down in the x direction, and that creates what we call a saddle point. So this is related to that table you made. We ignored in these examples the mixed partials because they happen to be 0 in all of these. They won't always. But here is our theorem for finding whether a critical point is a relative maximum or minimum for functions of two variables. We're going to calculate a new thing here, call it d. And it is the second partial derivative with respect to x at your point multiplied by the second partial derivative with respect to y, and then you subtract the mixed partial squared. So if that d ends up being a positive number, what that means then is depending on whether the second partial derivative is positive or negative, it's going to be a relative maximum or minimum. So if the second partial derivative is positive, that means we're concave up, so that's a relative minimum. Now you might notice here this mentions the second partial derivative with respect to x, but they're going to be the same sign. That's the only way you can get a positive here because you're subtracting the mixed. So the only way to get a positive is if the partial derivative, the second partial with respect to x and y are the same sign. All right, if the second partial is negative, then we have a relative maximum. If the d ends up being a negative number, the only way for that to happen is for the mixed partials to be opposites. Actually, no, I guess you could have, I'm trying to think here. So in our case, it happened because the second derivative with respect to x and the second derivative with respect to y were opposite signs. And that's most common. I suppose you could have a situation where those are the same, but then the second one, the mixed partial there is greater for some. I'm trying to think of an example offhand and I cannot. But this third case, if d is negative, is a saddle point. And like a lot of these tests, if you end up right on the threshold of 0, then the test doesn't work and you can conclude nothing. So let's go ahead and do an example here. This one is the critical points are a little more interesting than the last two, and then we're going to also try to determine whether they are saddle points or relative max, relative min. So let's find the partial derivative with respect to x. And let's see here. By the way, I had to switch to the headphones because they're a little less sensitive and kids were getting a little noisy in the background. So I apologize for having to stare at me in earbuds, but hopefully the audio will not be too much background noise, so that's all right. Second derivative with respect to y, let's see, we have 4x and then minus 4y. Now our critical points, we want both of these to be equal to 0. We want the partial derivative with respect to x, and we want the partial derivative with respect to y to both be equal to 0. So if we set negative 3x squared plus 4y equals 0, and then 4x minus 4y is equal to 0. If we want those both to be true, what we're really solving is a system of equations. Negative 3x squared plus 4y equals 0, and 4x minus 4y is equal to 0. And we're just going to use algebra from here to find the critical points, just by solving this system. What I would do is divide the second equation, both sides of it, by 4, and then add x, and what you get is that, or sorry, add y, you get that x is equal to y, and then use the substitution method. Let's see, if we did that, we'd have, I would substitute in, I guess it doesn't really matter because it will give us the same equation. If we substitute in x for y, we get negative 3x squared plus 4x equals 0. And then let's see here, factor out at x, negative 3x plus 4, and we get x is equal to 0, x is equal to positive 4/3. Now, remember, to find y when you did this in algebra, you might be tempted to go back and like re-solve it, substituting y in for x. Negative 3y squared plus 4y is equal to 0, and I get that temptation. You're going to get the same. The problem is you're not going to know, does 0 for x go with 0 for y? And does 0 for x go with 4/3 for y? Like, how do those points match up? So don't do that. Instead, go back to one of your original equations and use it to solve for y. And in fact, we know x is equal to y. So when x is 0, y is 0. When x is 4/3, y is equal to 4/3. And those are paired together. So we have the critical points 0, 0, and 4/3, 4/3. All right, now we're going to do the second partials test to determine whether they are relative max, relative min, or saddle points. We need some second partial derivatives. So let's find all three of those. The partial derivative of x with respect to, partial derivative of f with respect to x will be negative 6x. The mixed partial, if we take the derivative of that with respect to y, will be 4. And the second partial derivative of f with respect to y will be negative 4. So let's evaluate that at 0, 0. Now we'll have 0. Oops. 4. And negative 4. And then at 4/3, 4/3, at 4/3, 4/3, let's see, the 4. Sounds like it's going to be bad because you have some fractions here, but you just plug it in. Negative 6 times 4/3 is negative, almost said negative 12, negative 8. And then the mixed is constant, that's 4. And the second partial with respect to y, also constant, that is negative 4. All right, let's calculate the d for both of these cases. Here we have 0 times 4 minus negative 4. Nope, 0 times negative 4. Wouldn't have changed things, actually. Times 4 minus 4 squared, so we get negative 16. And here we have d equals negative 8 times 4. I did it again, times negative 4 minus 4 squared, and we'll get positive 16 for that one. So the first one, d is less than 0. That tells us that that is a saddle point. Saddle point. Now here we have greater than 0, so that means it's a relative minimum or relative maximum. We need to look at the second partial derivative with respect to x or y. Take a look at those. If we pick one of those, you'll see that they are both negative, either one. Fxx at 4/3. 4/3 is less than 0. So that means, where did my, right? They're both negative, concave down. So it is a relative maximum. Relative maximum. Let's finish this here. Write a nice answer here. F has a saddle point at 0, 0, and a relative maximum at 4/3, 4/3. All right, and let's take a look at that and finish the video taking a look at that in Maple. I've got another one up here. Let's take a look. Here is our function, and we can see at 4/3, 4/3, you can kind of take a look here. I don't know if you can see there, 4/3, 4/3. We have a relative maximum. And then at the origin, we have a saddle point. It's not a maximum, not a minimum. It is a saddle point there. And so that is the end of this video. In the next video, the last one from this section, we will talk about two particular optimization problems, kind of the classic box problem where you do that from Calc 1, except now we'll have a multivariable function that we will try to optimize.